Earth, third planet from the Sun and the fifth largest planet in the solar system in terms of size and mass. Its single most outstanding feature is that its near-surface environments are the only places in the universe known to harbor life. It is designated by the symbol, Earth's name in English, the international language of astronomy, derives from Old English and Germanic words for ground and earth, and it is the only name for a planet of the solar system that does not come from Greco-Roman mythology. Earth is part of the observable universe, the region of space that humans can actually or theoretically observe with the aid of technology. Unlike the observable universe, the universe is possibly infinite. Since the Copernican revolution of the 16th century, at which time the Polish astronomer Nicolaus Copernicus proposed a sun-centered model of the universe, see heliocentric system, enlightened thinkers have regarded Earth as a planet like the others of the solar system. Concurrent sea voyages provided practical proof that Earth is a globe, just as Galileo's use of his newly invented telescope in the early 17th century soon showed various other planets to be globes as well. It was only after the dawn of the space age, however, when photographs from rockets and orbiting spacecraft first captured the dramatic curvature of Earth's horizon, that the conception of Earth as a roughly spherical planet rather than as a flat entity was verified by direct human observation. Humans first witnessed Earth as a complete orb floating in the inky blackness of space in December 1968 when Apollo 8 carried astronauts around the moon. Robotic space probes on their way to destinations beyond Earth, such as the Galileo and the Near Earth Asteroid Rendezvous, NEAR spacecraft in the 1990s, also looked back with their cameras to provide other unique portraits of the planet. Viewed from another planet in the solar system, Earth would appear bright and bluish in color. Easiest to see through a large telescope would be its atmospheric features, chiefly the swirling white cloud patterns of mid-latitude and tropical storms, ranged in roughly latitudinal belts around the planet. The polar regions also would appear a brilliant white because of the clouds above and the snow and ice below. Beneath the changing patterns of clouds would appear the much darker blue-black oceans, interrupted by occasional tawny patches of desert lands. The green landscapes that harbor most human life would not be easily seen from space. Not only do they constitute a modest fraction of the land area, which itself is less than 1/3 of Earth's surface, but they are often obscured by clouds. Over the course of the seasons, some changes in the storm patterns and cloud belts on Earth would be observed. Also prominent would be the growth and recession of the winter snowcap across land areas of the northern hemisphere. Scientists have applied the full battery of modern instrumentation to studying Earth in ways that have not yet been possible for the other planets. Thus, much more is known about its structure and composition. This detailed knowledge, in turn, provides deeper insight into the mechanisms by which planets in general cool down, by which their magnetic fields are generated, and by which the separation of lighter elements from heavier ones as planets develop their internal structure releases additional energy for geologic processes and alters crustal compositions. Earth's surface is traditionally subdivided into 7 continental masses: Africa, Antarctica, Asia, Australia, Europe, North America, and South America. These continents are surrounded by 5 major bodies of water: the Arctic, Atlantic, Indian, Pacific, and Southern Oceans. However, it is convenient to consider separate parts of Earth in terms of concentric, roughly spherical layers. Extending from the interior outward, these are the core, the mantle, the crust, including the rocky surface, the hydrosphere, predominantly the oceans, which fill in low places in the crust, the atmosphere, itself divided into spherical zones such as the troposphere, where weather occurs, and the stratosphere, where lies the ozone layer that shields Earth's surface and its organisms against the sun's ultraviolet rays, and the magnetosphere, an enormous region in space where Earth's magnetic field dominates the behavior of electrically charged particles coming from the sun. Knowledge about these divisions is summarized in this astronomically oriented overview. The discussion complements other treatments oriented to the earth sciences and life sciences. Earth's figure and dimensions are discussed in the article Geodesy. Its magnetic field is treated in the article Geomagnetic field. The early evolution of the solid Earth and its atmosphere and oceans is covered in Geologic History of Earth. The geologic and biological development of Earth, including its surface features and the processes by which they are created and modified, are discussed in geochronology, continental landform, and plate tectonics. The behavior of the atmosphere and of its tenuous, ionized outer reaches is treated in atmosphere, while the water cycle and major hydrologic features are described in hydrosphere, ocean, and river. The solid Earth as a field of study is covered in geologic sciences. The methods and instruments employed to investigate Earth's surface and interior are discussed in Earth exploration, and the history of the study of Earth from antiquity to modern times is surveyed in Earth sciences. The global ecosystem of living organisms and their life-supporting stratum are detailed in biosphere. The mean distance of Earth from the Sun is about 149,600,000 kilometers, 92,960,000 miles. The planet orbits the Sun in a path that is presently more nearly a circle, less eccentric, than are the orbits of all but two of the other planets, Venus and Neptune. Earth makes one revolution, or one complete orbit of the Sun, in about 365.25 days. The direction of revolution, counterclockwise as viewed down from the north, is in the same sense, or direction, as the rotation of the Sun. Earth's spin, or rotation about its axis, is also in the same sense, which is called direct or prograde. The rotation period, or length of a sidereal day, C-day, sidereal time, 23 hours, 56 minutes, and 4 seconds, is similar to that of Mars. Jupiter and most asteroids have days less than half as long, while Mercury and Venus have days more nearly comparable to their orbital periods. The 23.44 degrees tilt, or inclination, of Earth's axis to its orbital plane, also typical, results in greater heating and more hours of daylight in one hemisphere or the other over the course of a year, and so is responsible for the cyclic change of seasons. With an equatorial radius of 6,378 kilometers, 3,963 miles, Earth is the largest of the 4 inner terrestrial, rocky planets, but it is considerably smaller than the gas giants of the outer solar system. Earth has a single natural satellite, the Moon, which orbits the planet at a mean distance of about 384,400 kilometers, 238,900 miles. The Moon is one of the bigger natural satellites in the solar system. Only the giant planets have moons comparable or larger in size. Some planetary astronomers consider the Earth-Moon system a double planet, with some similarity in that regard to the dwarf planet Pluto and its largest moon, Charon. Earth's gravitational field, sea gravitation, is manifested as the attractive force acting on a free body at rest, causing it to accelerate in the general direction of the center of the planet. Departures from the spherical shape and the effect of Earth's rotation cause gravity to vary with latitude over the terrestrial surface. The average gravitational acceleration at sea level is about 980 centimeters. Earth's gravity keeps the Moon in its orbit around the planet and also generates tides in the solid body of the Moon. Such deformations are manifested in the form of slight bulges at the lunar surface, detectable only by sensitive instruments. In turn, the Moon's mass, relatively large for a natural satellite, exerts a gravitational force that causes tides on Earth. The Sun, much more distant but vastly more massive, also raises tides on Earth. See celestial mechanics, tidal evolution. The tides are most apparent as the twice-daily and daily rises and falls of the ocean water, although tidal deformations occur in the solid Earth and in the atmosphere as well. See tide. The movement of the water throughout the ocean basins as a result of the tides, as well as, to a lesser extent, the tidal distortion of the solid Earth dissipates orbital kinetic energy as heat, producing a gradual slowing of Earth's rotation and a spiraling outward of the Moon's orbit. Currently, this slowing lengthens the day by a few thousandths of a second per century, but the rate of slowing varies with time as plate tectonics and sea level changes alter the areas covered by inland bays and shallow seas. For additional orbital and physical data, see the table. The The blankets of volatile gases and liquids near and above the surface of Earth are, along with solar energy, of prime importance to the sustenance of life on Earth. They are distributed and recycled throughout the atmosphere and hydrosphere of the planet. Earth is surrounded by a relatively thin atmosphere, commonly called air, consisting of a mixture of gases, primarily molecular nitrogen 78% and molecular oxygen 21%. Also present are much smaller amounts of gases such as argon, nearly 1%, water vapor averaging 1% but highly variable in time and location, carbon dioxide 395 parts per million, and presently rising. Methane, 0.00018%, 1.8 and presently rising, and others, along with minute solid and liquid particles in suspension. Because Earth has a weak gravitational field by virtue of its size and warm atmospheric temperatures due to its proximity to the Sun compared with the giant planets, it lacks the most common gases in the universe that they possess, hydrogen and helium. Whereas both the Sun and Jupiter are composed predominantly of these two elements, they could not be retained long on early Earth and rapidly evaporated into interplanetary space. The high oxygen content of Earth's atmosphere is out of the ordinary. Oxygen is a highly reactive gas that, under most planetary conditions, would be combined with other chemicals in the atmosphere, surface, and crust. It is in fact supplied continuously by biological processes. Without life, there would be virtually no free oxygen. The 1.8 parts per million of methane in the atmosphere is also far out of chemical equilibrium with the atmosphere and crust. It, too, is of biological origin, with the contribution by human activities far outweighing others. The gases of the atmosphere extend from the surface of Earth to heights of thousands of kilometers, eventually merging with the solar wind, a stream of charged particles that flows outward from the outermost regions of the Sun. The composition of the atmosphere is more or less constant with height to an altitude of about 100 kilometers 60 miles, with particular exceptions being water vapor and ozone. The atmosphere is commonly described in terms of distinct layers, or regions. Most of the atmosphere is concentrated in the troposphere, which extends from the surface to an altitude of about 10-15 kilometers, depending on latitude and season. The behavior of the gases in this layer is controlled by convection. This process involves the turbulent, overturning motions resulting from buoyancy of near-surface air that is warmed by the Sun. Convection maintains a decreasing vertical temperature gradient, i.e., a temperature decline with altitude, of roughly 6 degrees Celsius per kilometer through the troposphere. At the top of the troposphere, which is called the tropopause, temperatures have fallen to about 80 degrees C. The troposphere is the region where nearly all water vapor exists and essentially all weather occurs. The dry, tenuous stratosphere lies above the troposphere and extends to an altitude of about 50 kilometers. Convective motions are weak or absent in the stratosphere. Motions instead tend to be horizontally oriented. The temperature in this layer increases with altitude. In the upper stratospheric regions, absorption of ultraviolet light from the Sun breaks down molecular oxygen, O2. Recombination of single oxygen atoms with O2 molecules into ozone, O3, creates the shielding ozone layer. Above the relatively warm stratopause is the even more tenuous mesosphere, in which temperatures again decline with altitude to 80-90 kilometers above the surface, where the mesopause is defined. The minimum temperature attained there is extremely variable with season. Temperatures then rise with increasing height through the overlying layer known as the thermosphere. Also, above about 80-90 kilometers, there is an increasing fraction of charged or ionized particles, which from this altitude upward defines the ionosphere. Spectacular visible auroras are generated in this region, particularly along approximately circular zones around the poles, by the interaction of nitrogen and oxygen atoms in the atmosphere with episodic bursts of energetic particles originating from the Sun. Earth's general atmospheric circulation is driven by the energy of sunlight, which is more abundant in equatorial latitudes. Movement of this heat toward the poles is strongly affected by Earth's rapid rotation and the associated Coriolis force at latitudes away from the equator, which adds an east-west component to the direction of the winds, resulting in multiple cells of circulating air in each hemisphere. Instabilities, perturbations in the atmospheric flow that grow with time, produce the characteristic high-pressure areas and low-pressure storms of the mid-latitudes, as well as the fast, eastward-moving jet streams of the upper troposphere that guide the paths of storms. The oceans are massive reservoirs of heat that act largely to smooth out variations in Earth's global temperatures, but their slowly changing currents and temperatures also influence weather and climate, as in the El Niño Southern Oscillation weather phenomenon. Earth's atmosphere is not a static feature of the environment. Rather, its composition has evolved over geologic time in concert with life and is changing more rapidly today in response to human activities. Roughly halfway through the history of Earth, the atmosphere's unusually high abundance of free oxygen began to develop, through photosynthesis by cyanobacteria and saturation of natural surface sinks of oxygen. For example, relatively oxygen-poor minerals and hydrogen-rich gases exuded from volcanoes. Accumulation of oxygen made it possible for complex cells, which consume oxygen during metabolism, and of which all plants and animals are composed, to develop. Earth's climate at any location varies with the seasons, but there are also longer-term variations in global climate. Volcanic explosions, such as the 1991 eruption of Mount Pinatubo in the Philippines, can inject great quantities of dust particles into the stratosphere, which remain suspended for years, decreasing atmospheric transparency and resulting in measurable cooling worldwide. Much rarer, giant impacts of asteroids and comets can produce even more profound effects, including severe reductions in sunlight for months or years, such as many scientists believe led to the mass extinction of living species at the end of the Cretaceous period, 66 million years ago. For additional information on the risks posed by cosmic impacts and the chances of their occurrence, see Earth impact hazard. The dominant climate variations observed in the recent geologic record are the ice ages, which are linked to variations in Earth's tilt and its orbital geometry with respect to the Sun. The physics of hydrogen fusion leads astronomers to conclude that the Sun was 30% less luminous during the earliest history of Earth than it is today. Hence, all else being equal, the oceans should have been frozen. Observations of Earth's planetary neighbors, Mars and Venus, and estimates of the carbon locked in Earth's crust at present suggest that there was much more carbon dioxide in Earth's atmosphere during earlier periods. This would have enhanced warming of the surface via the greenhouse effect, and so allowed the oceans to remain liquid. Today, there is 100,000 times more carbon dioxide buried in carbonate rocks in Earth's crust than in the atmosphere, in sharp contrast to Venus, whose atmospheric evolution followed a different course. On Earth, the formation of carbonate shells by marine life is the principal mechanism for transforming carbon dioxide to carbonates. Abiotic processes involving liquid water also produce carbonates, albeit more slowly. On Venus, however, life never had the chance to arise and to generate carbonates. Because of the planet's location in the solar system, early Venus received 10–20% more sunlight than falls on Earth even today, despite the fainter young sun at the time. Most planetary scientists believe that the elevated surface temperature that resulted kept water from condensing to a liquid. Instead, it remained in the atmosphere as water vapor, which, like carbon dioxide, is an efficient greenhouse gas. Together, the two gases caused surface temperatures to rise even higher, so that massive amounts of water escaped to the stratosphere, where it was dissociated by solar ultraviolet radiation. With conditions now too hot and dry to permit abiotic carbonate formation, most or all of the planet's inventory of carbon remained in the atmosphere as carbon dioxide. Models predict that Earth may suffer the same fate in 1 billion years, when the sun exceeds its present brightness by 10–20%. Between the late 1950s and the end of the 20th century, the amount of carbon dioxide in Earth's atmosphere increased by more than 15% because of the burning of fossil fuels and the destruction of tropical rainforests, such as that of the Amazon River basin. Computer models predict that a net doubling of carbon dioxide by the middle of the 21st century could lead to a global warming of averaged over the planet, which would have profound effects on sea level and agriculture. Although this conclusion has been criticized by some on the basis that the warming observed so far has not kept pace with the projection, Analyses of ocean temperature data have suggested that much of the warming during the 20th century actually occurred in the oceans themselves and will eventually appear in the atmosphere. Earth's hydrosphere is a discontinuous layer of water at or near the planet's surface. It includes all liquid and frozen surface waters, groundwater held in soil and rock, and atmospheric water vapor. Unique within the solar system, the hydrosphere is essential to all life as it is presently understood. Earth has a surface area of roughly 510,066,000 square km. Almost 71% of Earth's surface is covered by saltwater oceans. The total volume of liquid water on Earth is about 1.39 billion cubic km, 332.5 million cubic miles, and it has an average temperature of about 4 degrees Celsius, not far above the freezing point of water. The oceans contain about 97% of the planet's water volume. The remainder occurs as fresh water, 3/4 of which is locked up in the form of ice at polar latitudes. Most of the remaining fresh water is groundwater held in soils and rocks. Less than 1% of it occurs in lakes and rivers. In terms of percentage, atmospheric water vapor is negligible, but the transport of water evaporated from the oceans onto land surfaces is an integral part of the hydrologic cycle that renews and sustains life. The hydrologic cycle involves the transfer of water from the oceans through the atmosphere to the continents and back to the oceans over and beneath the land surface. The cycle includes processes such as precipitation, evaporation, transpiration, infiltration, percolation, and runoff. These processes operate throughout the entire hydrosphere, which extends from about 15 kilometers into the atmosphere to roughly 5 kilometers into the crust. About 1/3 of the solar energy that reaches Earth's surface is expended on evaporating ocean water. The resulting atmospheric moisture and humidity condense into clouds, rain, snow, and dew. Moisture is a crucial factor in determining weather. It is the driving force behind storms and is responsible for separating electrical charge, which is the cause of lightning and thus of natural wildland fires, which have an important role in some ecosystems. Moisture wets the land, replenishes subterranean aquifers, chemically weathers the rocks, erodes the landscape, nourishes life, and fills the rivers, which carry dissolved chemicals and sediments back into the oceans. Water also plays a vital role in the carbon dioxide cycle, a part of the more inclusive carbon cycle. Under the action of water and dissolved carbon dioxide, calcium is weathered from continental rocks and carried to the oceans, where it combines to form calcium carbonates, including shells of marine life. Eventually, the carbonates are deposited on the seafloor and are lithified to form limestones. Some of these carbonate rocks are later dragged deep into Earth's interior by the global process of plate tectonics, see below the outer shell, and melted, resulting in a re-release of carbon dioxide from volcanoes, for example, into the atmosphere. Cyclic processing of water, carbon dioxide, and oxygen through geologic and biological systems on Earth has been fundamental to maintaining the habitability of the planet with time and to shaping the erosion and weathering of the continents, and it contrasts sharply with the lack of such processes on Venus. Evidence of past episodes of liquid water erosion, and possibly limited amounts of such erosion today, has been found on Mars. Earth's outermost, rigid, rocky layer is called the crust. It is composed of low-density, easily melted rocks. The continental crust is predominantly granitic rock, while composition of the oceanic crust corresponds mainly to that of basalt and gabbro. Analyses of seismic waves, generated by earthquakes within Earth's interior, show that the crust extends about 50 kilometers beneath the continents, but only 5–10 kilometers beneath the ocean floors. At the base of the crust, a sharp change in the observed behavior of seismic waves marks the interface with the mantle. The mantle is composed of denser rocks, on which the rocks of the crust float. On geologic timescales, the mantle behaves as a very viscous fluid and responds to stress by flowing. Together, the uppermost mantle and the crust act mechanically as a single rigid layer, called the lithosphere. The lithospheric outer shell of Earth is not one continuous piece, but is broken, like a slightly cracked eggshell, into about a dozen major separate rigid blocks, or plates. There are two types of plates, oceanic and continental. An example of an oceanic plate is the Pacific Plate, which extends from the East Pacific Rise to the deep sea trenches bordering the western part of the Pacific Basin. A continental plate is exemplified by the North American Plate, which includes North America as well as the oceanic crust between it and a portion of the Mid-Atlantic Ridge. The latter is an enormous submarine mountain chain that extends down the axis of the Atlantic Basin, passing midway between Africa and North and South America. The lithospheric plates are about 60 kilometers thick beneath the oceans and 100-200 kilometers beneath the continents. It should be noted that these thicknesses are defined by the mechanical rigidity of the lithospheric material. They do not correspond to the thickness of the crust, which is defined at its base by the discontinuity in seismic wave behavior, as cited above. They ride on a weak, perhaps partially molten layer of the upper mantle called the asthenosphere. Slow convection currents deep within the mantle generated by radioactive heating of the interior drive lateral movements of the plates and the continents on top of them at a rate of several centimeters per year. The plates interact along their margins, and these boundaries are classified into three general types on the basis of the relative motions of the adjacent plates: divergent, convergent, and transform or strike-slip. In areas of divergence, two plates move away from each other. Buoyant upwelling motions in the mantle force the plates apart at rift zones, such as along the middle of the Atlantic Ocean floor, where magmas from the underlying mantle rise to form new oceanic crustal rocks. Lithospheric plates move toward each other along convergent boundaries. When a continental plate and an oceanic plate come together, the leading edge of the oceanic plate is forced beneath the continental plate and down into the asthenosphere, a process called subduction. Only the thinner, denser slabs of oceanic crust will subduct, however. When two thicker, more buoyant continents come together at convergent zones, they resist subduction and tend to buckle, producing great mountain ranges. The Himalayas, along with the adjacent plateau of Tibet, were formed during such a continent-continent collision, when India was carried into the Eurasian plate by relative motion of the Indian-Australian plate. At the third type of plate boundary, the transform variety, two plates slide parallel to one another in opposite directions. These areas are often associated with high seismicity, as stresses that build up in the sliding crustal slabs are released at intervals to generate earthquakes. The San Andreas Fault in California is an example of this type of boundary, which is also known as a fault or fracture zone, see submarine fracture zone. Most of Earth's active tectonic processes, including nearly all earthquakes, occur near plate margins. Volcanoes form along zones of subduction because the oceanic crust tends to be remelted as it descends into the hot mantle and then rises to the surface as lava. Chains of active, often explosive volcanoes are thus formed in such places as the Western Pacific and the west coasts of the Americas. Older mountain ranges, eroded by weathering and runoff, mark zones of earlier plate margin activity. The oldest, most geologically stable parts of Earth are the central cores of some continents such as Australia, parts of Africa, and northern North America. Called continental shields, they are regions where mountain building, faulting, and other tectonic processes are diminished compared with the activity that occurs at the boundaries between plates. Because of their stability, erosion has had the time to flatten the topography of continental shields. It is also on the shields that geologic evidence of crater scars from ancient impacts of asteroids and comets is better preserved. Even there, however, tectonic processes and the action of water have erased many ancient features. In contrast, much of the oceanic crust is substantially younger, tens of millions of years old, and none dates back more than 200 million years. This conceptual framework in which scientists now understand the evolution of Earth's lithosphere, termed plate tectonics, is almost universally accepted, although many details remain to be worked out. For example, scientists have yet to reach a general agreement as to when the original continental cores formed or how long ago modern plate tectonic processes began to operate. Certainly the processes of internal convection, segregation of minerals by partial melting and recrystallization, and basaltic volcanism were operating more vigorously in the first billion years of Earth's history, when the planet's interior was much hotter than it is today. Nevertheless, how the surface landmasses were formed and were dispersed may have been different. Once major continental shields grew, plate tectonics was characterized by the cyclic assembly and breakup of supercontinents created by the amalgamation of many smaller continental cores and island arcs. Scientists have identified 2 such cycles in the geologic record. A supercontinent began breaking up about 700 million years ago, in late Precambrian time, into several major continents, but by about 250 million years ago, near the beginning of the Triassic period, the continued drifting of these continents resulted in their fusion again into a single supercontinental landmass called Pangaea. Some 70 million years later, Pangaea began to fragment, gradually giving rise to today's continental configuration. The distribution is still asymmetric, with continents predominantly located in the northern hemisphere opposite the Pacific Basin. Startlingly, of the 4 terrestrial planets, only Earth shows evidence of long-term, pervasive plate tectonics. Both Venus and Mars exhibit geology dominated by basaltic volcanism on a largely immovable crust, with only faint hints of possibly limited episodes of horizontal plate motion. Mercury is intrinsically much denser than the other terrestrial planets, which implies a larger metallic core. Its surface is mostly covered with impact craters, but it also shows a global pattern of scarps, suggesting shrinkage of the planet, associated perhaps with interior cooling. Apparently essential to the kind of plate tectonics that occurs on Earth are large planetary size, hence high heat flow and thin crust, which eliminates Mars, and pervasive crustal water to soften the rock, which Venus lost very early in its history. Although Earth is indeed geologically active and hence possesses a youthful surface, Venus's surface may have been completely renewed by global basaltic volcanism within the past billion years, and small portions of Mars's surface may have experienced very recent erosion from liquid water or landslides. More than 90% of Earth's mass is composed of iron, oxygen, silicon, and magnesium, elements that can form the crystalline minerals known as silicates. Nevertheless, in chemical and mineralogical composition, as in physical properties, Earth is far from homogeneous. Apart from the superficial lateral differences near the surface, Earth's principal differences vary with distance toward the center. This is due to increasing temperatures and pressures, and to the original segregation of materials soon after Earth accreted from the solar nebula about 4.56 billion years ago into a metal-rich core, a silicate-rich mantle, and the more highly refined crustal rocks. Earth is geochemically differentiated to a great extent. Crustal rocks contain several times as much of the rock-forming element aluminum as does the rest of the solid Earth, and many dozens of times as much uranium. On the other hand, the crust, which accounts for a mere 0.4% of Earth's mass, contains less than 0.1% of its iron. Between 85 and 90% of Earth's iron is concentrated in the core. The increasing pressure with depth causes phase changes in crustal rocks at depths between 5 and 50 kilometers, which marks the top of the upper mantle, as mentioned above. This transition area is called the Mohorovičić discontinuity, or MOHO. Most basaltic magmas are generated in the upper mantle at depths of hundreds of kilometers. The upper mantle, which is rich in the olivine, pyroxene, and silicate perovskite minerals, shows significant lateral differences in composition. A large fraction of Earth's interior, from a depth of about 650 kilometers down to 2,900 kilometers, consists of the lower mantle, which is composed chiefly of magnesium and iron-bearing silicates, including the high-pressure equivalents of olivine and pyroxene. The mantle is not static, but rather churns slowly in convective motions, with hotter material rising up and cooler material sinking. Through this process, Earth gradually loses its internal heat. In addition to being the driving force of horizontal plate motion, mantle convection is manifested in the occurrence of temporary superplumes, huge rising jets of hot, partially molten rock, which may originate from a deep layer near the core mantle interface. Much larger than ordinary thermal plumes, such as that associated with the Hawaiian island chain in the Central Pacific, see volcano, intraplate volcanism, Superplumes may have had profound effects on Earth's geologic history and even on its climate. One outburst of global volcanism about 66 million years ago, which created the vast flood basalt deposits known as the Deccan Traps on the Indian subcontinent, may have been associated with a superplume, though this model is far from universally accepted. With a radius of almost 3,500 kilometers, Earth's core is about the size of the entire planet Mars. About 1/3 of Earth's mass is contained in the core, most of which is liquid iron alloyed with nickel and some lighter, cosmically abundant components, sulfur, oxygen, and controverse. Its liquid nature is revealed by the failure of shear-type seismic waves to penetrate the core. A small central part of the core, however, below a depth of about 5,100 kilometers, is solid iron. This inner core is itself divided into two layers, known only by the polarity differences of the iron crystals found within them. The polarity of the iron crystals of the innermost layer is oriented in an east-west direction, whereas that of the outermost layer is oriented north-south. Temperatures in the core are extremely hot, ranging from 4,000–5,000 K at the outer part of the core to 5,000–7,000 K in the center, comparable to the surface of the Sun. Large uncertainties in temperature arise from questions as to which compounds form alloys with iron in the core, and more recent data favor the lower end of the temperature estimates for the inner core. The core's reservoir of heat may contribute as much as 1/5 of all the internal heat that ultimately flows to the surface of Earth. The basic structure of Earth, crust, mantle, and core, appears to be replicated on the other terrestrial planets, though with substantial variations in the relative size of each region. Helical fluid motions in Earth's electrically conducting liquid outer core have an electromagnetic dynamo effect, giving rise to the geomagnetic field. The planet's sizable, hot core, along with its rapid spin, probably accounts for the exceptional strength of the magnetic field of Earth compared with those of the other terrestrial planets. Venus, for example, which has a metallic core that may be similar to Earth's in size, rotates very slowly and has no detected intrinsic magnetic field. Mercury and Mars have only small intrinsic magnetic fields. Earth's main magnetic field permeates the planet and an enormous volume of space surrounding it. A great teardrop-shaped region of space called the magnetosphere is formed by the interaction of Earth's field with the solar wind. At a distance of about 65,000 kilometers outward toward the Sun, the pressure of the solar wind is balanced by the geomagnetic field. This serves as an obstacle to the solar wind, and the flow of charged particles, or plasma, is deflected around Earth by the resulting bow shock. The magnetosphere so produced streams out into an elongated magnetotail that stretches several million kilometers downstream from Earth away from the Sun. Plasma particles from the solar wind can leak through the magnetopause, the sunward boundary of the magnetosphere, and populate its interior. Charged particles from the Earth's ionosphere also enter the magnetosphere. The magnetotail can store for hours an enormous amount of energy, several billion megajoules, which is roughly equivalent to the yearly electricity production of many smaller countries. This occurs through a process called reconnection, in which the Sun's magnetic field, dragged into interplanetary space by the solar wind, becomes linked with the magnetic field in Earth's magnetosphere. The energy is released in dynamic structural reconfigurations of the magnetosphere, called geomagnetic substorms, which often result in the precipitation of energetic particles into the ionosphere, giving rise to fluorescing auroral displays. Converging magnetic field lines fairly close to Earth can trap highly energetic particles so that they gyrate between the northern and southern hemispheres and slowly drift longitudinally around the planet in two concentric donut-shaped zones known as the Van Allen radiation belts. Many of the charged particles trapped in these belts are produced when energetic cosmic rays strike Earth's upper atmosphere, producing neutrons that then decay into electrons, which are negatively charged, and protons, which are positively charged. Others come from the solar wind or Earth's atmosphere. The inner radiation belt was detected in 1958 by the American physicist James Van Allen and colleagues using a Geiger-Miller counter aboard the first U.S. satellite, Explorer 1. The outer belt was distinguished by other US and Soviet spacecraft launched the same year. Earth's magnetosphere has been extensively studied ever since, and space physicists have extended their studies of plasma processes to the vicinities of comets and other planets. For additional information on the interaction of the Sun and Earth's charged particles and magnetic fields. An important characteristic of Earth's magnetic field is polarity reversal. In this process, the direction of the dipole component reverses, i.e., the north magnetic pole becomes the south magnetic pole and vice versa. From studying the direction of magnetization of many rocks, geologists know that such reversals occur, without a discernible pattern, at intervals that range from tens of thousands of years to millions of years, though they are still uncertain about the mechanisms responsible. It is likely that during the changeover, which is believed to take a few thousand years, a non-dipolar field remains at a small fraction of the strength of the normal field. In the temporary absence of the dipole component, the solar wind would approach much closer to Earth, allowing particles that are normally deflected by the field or are trapped in its outer portions to reach the surface. The increase in particle radiation could lead to increased rates of genetic damage and thus of mutations or sterility in plants and animals, leading to the disappearance of some species. Scientists have looked for evidence of such changes in the fossil record at times of past field reversals, but the results have been inconclusive. The origin of Earth in its present form has long been the subject of intellectual interest, but since the mid-20th century, scientists have made particularly significant advances, both in concepts and in measurements. Analysis of the isotopes in meteorites, and in particular, of rocks brought back from the Moon by U.S. Apollo astronauts, have produced some of the major contributions. Other gains have come from geochemical research on terrestrial samples, combined with the new understanding of internal processes brought on by the recognition of plate tectonics, study of the terrestrial planets as a group, and advances in numerical modeling of the physical processes that lead to planetary formation.